Okay, we will find out electric field intensity due to surface charge distribution. For that we are considering surface charge which is placed along xy plane, and in xy plane surface charge is uniformly placed in infinite region. So for xy plane there is a limit for x and y, that is from minus infinity to infinity. So we will consider surface charge density, that is rho s. Surface charge density rho s, which is nothing but total charge divided by total area, which can be expressed, that is coulomb per meter square. This will be the unit. And q is nothing but total charge, s is nothing but surface area. So consider surface area in xy plane, and I will draw this diagram. So I have considered that diagram in space. Okay, so consider this is xy plane. Let me take pen. Okay, this is x. This is surface charge density rho s, which is placed in xy plane. This is x. This is y. This is z. X, y, z axis, and this is infinite sheet of charge, which is surface charge distribution rho s. So we will consider point P on the positive direction of z-axis, that is P. In Cartesian coordinate system, P can be located with the help of components in respective axis, that is x, y, z component. As P lies on positive direction of z-axis, x and y components of that point will be zero, and z, we have considered here z is component in the z direction. These component coordinates in rectangular coordinate system, if we convert or we consider that coordinate in the cylindrical coordinate system, then it will become rho phi z. As P lies on z axis, rho is equal to 0, so we can again define that point 0 phi z. So phi has any value because it lies on z axis, and phi is nothing but angle with respect to x axis. So we can take phi for any value for this point P. So we have got point P here, that is nothing but 0 phi z. Okay, so consider a differential surface area in xy plane at which this is differential surface area, and at which there is a dq amount of charge is placed. Dq amount of charge is placed. So what will be the value of dq? What will be value of dq? Dq will be is equal to rho s into ds, where ds is differential surface area. This is s. Consider this is s. Okay, rho s into ds, where dq is a differential or a small amount of charge which is placed on differential element or differential surface area ds. Okay, so we will find out electric field intensity due to ds at point P, which is equal to dE, and with the help of this diagram I can write down here dE bar. This is differential electric field intensity denoted by this point, this vector. Okay, this is vector which will give the differential electric field intensity due to this differential surface area dE. Okay, and what will be the direction of that differential electric field intensity? That will be denoted by this vector. So if you consider a component of dE in vertical and horizontal plane, horizontal direction, so these are two components. These are two components, that is, this is in the direction of z, and this will be in the direction of rho. Okay, this will be in the direction of rho, this will be in the direction of z. So if you consider exact opposite differential surface area for this ds, so it will lie on another part, that is ds dash. If you consider difference exact opposite differential surface area, which is also contain dq amount of charge, then due to that differential surface area there will be differential electric field intensity or dE at point P. Okay, which can be denoted with the help of this vector dE. And this differential electric field intensity has also two components, that is in in the direction of z and in the direction of rho. So if you see here, there are two differential electrical intensity due to same amount of charge but placed on exact opposite differential surface areas present on xy plane. There will be differential electrical intensity at point P, which is in which will be of course same in magnitude but differs in direction. If we resolve that differential electrical intensity in horizontal and vertical component, we will see rho component or electrical intensity in the direction of rho will get cancelled out, and only remaining part of electrical intensity or effective electrical intensity will be in the direction of z. Okay, will be in the direction of z. So we will write down equation for dE. Okay, we will write down differential electrical intensity dE. Okay, first I will write down here dq. dq, what will be dq? dq will be multiplication of surface charge density into differential surface area. Okay, and what will be dE? dE will be differential electrical intensity due to surface charge ds. Okay, and that will be defined dq divided by 4 pi epsilon r square ar cap, where r is nothing but distance of vector. Okay, r is nothing but distance of dq, distance of dq and point, distance of dq and point at which we are calculating electrical intensity, in our case point P. Okay, r is nothing but distance of between dq and point P. So we will calculate distance between both of them. Okay, this is point P, this is dq, charge placed in differential surface area here. So what will be the distance? It will be r, and vector r is nothing but, this is vector r. So what will be the vector r? We can define vector r with the help of this component, that is 0 minus, actually we need to define coordinates for this point also, dq point also. It will be in xy plane. In Cartesian coordinate system, it will be equal to x, y and 0, but in case of cylindrical coordinate system, it will be rho phi 0, because it lies in xy plane, so there will be no component in the direction of z. So for this point, or we can say for dq, rho phi 0, these are the components in rectangular cylindrical coordinate system. So now we can write down r vector. How to find out? 0 minus rho, that will be minus rho, and unit vector in the cylindrical coordinate system, it will be a rho, plus phi minus phi, it will be come out 0, z minus 0, z a z cap. So r is nothing but, r bar is nothing but rho a rho plus z a z cap, where rho is, this first term is negative, minus rho a rho plus z a z cap. So we have calculated r bar So we can also calculate unit vector in the direction of r and magnitude of r. So I will change this slide. Okay, so calculate unit vector ar. So first we need to write down r bar. What is r bar? We have calculated right now, that is a rho plus z az cap. So what will be ar cap? It is nothing but unit vector in the direction of r. So we can calculate a rho plus z az cap divided by magnitude of r, which will come out minus rho a rho plus z az cap divided by under root square rho square plus z square. So we'll calculate dE, and in dE we will place dq as a rho is ds. Ar cap is equal to minus rho a rho plus z az cap, and r is nothing but magnitude, so we will take magnitude of r is nothing but rho square plus z square under root. So we will write down expression for dE, which is nothing but electric field intensity dE bar dq divided by 4 pi epsilon 0 r square ar cap. We can replace dq with the help of rho s ds divided by 4 pi epsilon. We replace r square with the help of under root rho square plus z square raised to 2 into ar cap a rho plus z az cap divided by under root rho square plus z square. So we will evaluate this expression rho s ds into minus rho a rho cap plus z az cap divided by 4 pi epsilon 0 rho square plus z square raised to 3 by 2. Okay, so this is nothing but dE bar electric field intensity. There are two terms here. If you see minus rho a rho, this is minus rho a rho plus z az. So we can also split this term for dE bar. First term will come out rho s ds into minus rho a rho divided by denominator, that is 4 pi epsilon rho square plus z square raised to 3 plus the second term will rho s ds minus rho a rho plus, sorry, we have taken this term first term. The only remaining part will be z az cap divided by 4 pi epsilon rho square plus z square raised to 3 by 2. Okay, so we can say that differential electric field intensity dE bar has two terms, that is the first term which is in the direction of a rho and second term which is in the direction of z. As we have studied or we have seen last diagram, okay, just consider this diagram. There will be two components of dE, that is in the direction of z and in the direction of rho. Similarly, the differential electric field intensity due to exact opposite differential surface area present over here, that is also has two components, that is one component in the direction of z and another component in the direction of rho. So rho get cancelled, so differential electric field intensity has only effective component which is in the direction of z. So we can take or we can ignore the last term or the first term which is in the direction of rho, and only we will consider this term for our further calculations. Before that, I will note down here. Let me take pen. Okay, this is nothing but electric field intensity in the direction of rho, and this term which is nothing but electric field intensity in the direction of z. So we will only consider electric field intensity in the direction of z. So we will write down here DEZ, that is electric field intensity in the direction of Z, which will be nothing but rho S ds into Z A Z cap divided by 4 pi epsilon r raised to 3 by 2, means rho square plus Z square raised to 3 by 2. Okay, because we have not considered the first term, that is in the direction of rho. So this is nothing but the electric field intensity in the direction of Z axis, and rho s ds into Z az divided by 4 pi epsilon 4 rho square plus Z square raised to 3 by 2. This is the exact amount. Okay. So we will calculate further az cap. Okay. So before that, we need to define the S bar, or we need to take a value of ds bar. If you remember that we have studied differential length, differential surface area, and differential volume in all coordinate system. That is, in case of rectangular coordinate system, differential lengths are dx, dy, dz, and differential surface areas are dx into dy, dy into dz, or dz into dx. And differential volume in case of rectangular coordinate system, which is nothing but multiplication of our differential lengths, that is dx, dy, dz. Similarly, let me show you. A differential surface area in cylindrical coordinate system. Okay, we have studied in very first lecture. Okay, this diagram. Consider this diagram. These are the differential volume in cylindrical coordinate system. If you consider this is rho, and increment in rho is d rho. This is z, and increment in z is dz, and in the direction of phi, that is this angle, and the initial angle is phi, and differential angle we have added here, that is d phi. So due to increment in all direction, there will be a differential volume, and for that differential length we have calculated, that is in the direction of rho. Rho is nothing but length, or actual distance of that point from z axis. So differential length for or in the direction of rho, it will be d rho, and it will in the direction of z, it will be dz, but in the direction of phi, because this is angle, so differential length or is nothing but rho into d phi. Okay, so in our case we have considered, so just consider this diagram. In our case we have considered a differential surface area in xy plane. So what will be the value of differential surface area if you consider in the xy plane? This will be this differential surface area, which is projected on xy plane. Okay, I think you're getting this. Okay, I consider this you're getting this. We need to find out this differential. Let me annotate here. Okay, we need to find out this differential surface area. And what will be differential surface area? Multiplication of this side and multiplication of this side. This side is nothing but rho into d phi, and this side is nothing but d rho. So differential surface area is nothing but, in our case, which is in xy plane, is nothing but multiplication of rho d phi and multiplication of d rho, because this is slide, this side and this side we need to multiply. So what will be differential surface area? It will be rho d phi d rho. Okay, so we will calculate ds. Ds will be rho rho d rho d phi. Okay, so what will be effective equation or expression? It will be dz rho s ds will be replaced by rho d rho d phi z a z cap divided by 4 pi epsilon 0 rho square plus z square raised to 3 by 2. Okay, now we have got a differential electric field intensity in the direction of z axis, and which can be explained with the help of this expression. So now we will find out electric field intensity at point P uh, due to entire or due to entire charge distribution which is placed along x-axis. So for we need to take integration of this equation. We have calculated or we have derived here dEz for entire limit. Okay, so there are differential elements present here, d rho and d phi. So we need to take integration, surface integration of this expression in the limit of rho and phi. So what will be the limit of rho? Rho is nothing but radius of cylinder, or we can say distance of any point from z-axis, which is nothing but which will be minimum 0 and which will be maximum up to infinite. And what will be limit of phi? Phi has limit of, let me note down here, phi rho has limit of 0 to infinity. Okay, limit of rho, and for phi it will be from 0 to 2 pi. Okay, so we need to integrate this expression within this limit, so we will get effective electric field intensity or total electric field intensity at point P due to entire surface charge distribution. So I will integrate this expression to find out electric field intensity. What will be E? E will be integration of our last expression. E will be electric field intensity at point P, and what will be the limit? We need to find out surface integral, so there double integration. And what was the rho s into ds? Ds is nothing but rho d phi into az az cap divided by 4 pi epsilon 0 rho square plus z square raised to 3 by 2. Okay, we can say az cap, which is nothing but a perpendicular vector to the surface charge distribution. Okay, so we can replace az cap with a generalized term. We can say an cap. Okay, az cap we can replace, but before that we need to specify limits. For limit rho it will be from 0 to infinity, and for phi it will be from 0 to 2 pi. Okay, so we will calculate here. We will take first common terms here, rho s into z az cap divided by 4 pi epsilon 0. What will be integration of phi d phi? It will be phi, and just put limit here 0 to 2 pi. The remaining integration will be 0 to infinity rho divided by rho square plus z square raised to 3 by 2 d rho. Okay, this will be the remaining integration. So we will solve the first integration here. Rho s into z az cap divided by 4 pi epsilon 0 into 2 pi minus 0 into 2 pi, and remaining part will be, we will calculate here, we will 0 to infinite rho divided by rho square plus z square raised to 3 by 2 d rho. Okay, so pi gets cancelled to 2. I'll change the slide. Let me take a new slide. Okay, what was last term? That is rho is z a z cap divided by 2 epsilon 0, 2 epsilon 0, and this integration. So we will calculate here E bar. E bar or electrical intensity rho s z a z cap divided by 2 epsilon 0. Okay, and integration from 0 to 2 pi, 0 to 2 pi rho divided by rho square plus z square raised to 3 by 2 d rho. Okay, so we will calculate this term. Just post z is equal to r square plus z square. Rho square plus z square will be equal to k. Okay, we will consider rho square plus z square is equal to k. So we will differentiate this term. That is 2 rho d rho is equal to dk. So what will be value of d rho? D rho will be dk by 2 rho. So we will change this variable. So what will be the integration of, just before that we need to change the limit. If you consider rho square plus z square is equal to k, and if you differentiate this term, 2 rho d rho is equal to dk. So d rho will be dk divided by 2 rho. Okay, so we need to change limit also. If we rho is equal to 0, so k will be z square. Okay, so I'll check here first, 1 second. Okay, from this equation we can check, if we put, if rho is equal to 0, then k is equal to z square, and if rho is equal to infinite, k is equal to infinite. Okay, you can check here, it's very simple. If you put rho is equal to 0, k is equal to z square, and if we take rho is equal to infinite, k will be infinite. So our integration is becomes very simple one. So we will find out whole integration. Z k square into infinite into rho divided by rho square plus z square. We have converted it into, just let me check previous slide. Okay, rho square we have converted rho d rho. Rho d rho means dk by 2. We have to put rho d rho into dk by 2. Okay, so we don't need to replace only d rho, we need to replace rho into d rho. Okay, so just check here. We will replace rho d rho, only calculate rho d rho. Rho d rho is equal to dk by 2. So in next slide, just let me erase first. I will write down first equation here, and after that I will solve. The original equation is 0 to infinite rho divided by rho square plus z square raised to 3 by 2 d rho, and if we put rho square plus z square is equal to k, so 2 rho d rho is equal to dk. So rho d rho will be equal to dk by 2, and limit rho is equal to 0, then k is equal to z square, and rho is equal to infinity, or rho is tends to infinity, then k also tends to infinity. So we will replace this part here. 0 means z square to infinite, rho d rho means dk by 2, and what will be the denominator? Rho square plus z square is k raised to 3 by 2. Okay, we will solve this expression. Dk by 2, it will be equal to z square plus infinite k raised to minus 3 by 2. It will be equal to k raised to minus 3 by 2 dk divided by 2. So what will be the integration? It will be equal to half into k raised to minus 3 by 2 plus 1 divided by minus 3 by 2 plus 1. So it will turn out half into half minus half. Denominator will be minus half and k raised to minus half. So half get, sorry, limit we have ignored limit actually here. Z square to infinite. Here also z square to infinite. So half get cancel, half get cancel. There will be only negative signs remaining. Minus 1. I'll write down here. K raised to half is 1 upon root k. It will become 1 upon root k. That is z square and infinite. Right. So what will be the term? Minus 1 into 1 upon root k. 1 upon root k z square raised to infinite. If you put here infinite, it will become 0. 0 minus 1 upon z. 0 minus 1 upon z. It will become 0 minus 1 upon z. If you solve this integration with the limit, if you get 0 minus 1 upon z, and it will equal to, it will be ultimately equal to minus into minus plus 1 upon z plus 1 upon z. So integration of this term is nothing but 1 upon z. 1 upon z. So we will consider last expression here. So integration of this term is nothing but 1 upon z. Okay, so e bar will be equal to e bar ultimately e bar will be equal to rho s z a z cap. Just consider this step, divided by 2 epsilon 0 into integration of this term. Okay, this term will be 1 upon z. So z get cancelled out. So the remaining part will be rho s a z cap divided by 2 epsilon 0. We can generalize this unit vector, that is this unit vector is in the direction of z axis. We can take a normal component as a generalized vector, because z is nothing but a normal or a perpendicular unit vector to the xy plane, which is nothing but we have placed a charge across xy plane. So we can generalize the electric field intensity expression here. We can write down that equation we have calculated right now, that is E bar is equal to rho s divided by 2 epsilon 0 into a z cap, which is nothing but rho s divided by 2 epsilon 0 a n, where a n is nothing but normal component or normal vector, a perpendicular vector to the surface charge distribution. Okay, we will stop here.